In the White Mountains of California, a tree is still breathing that was already ancient when the pyramids were built. Its wood is twisted, its bark worn thin by millennia of wind, and yet it lives. Tonight, we will sit beside this tree and listen to the story held within its rings, a story older than almost every civilization that has ever risen and fallen on this earth. Let yourself settle in, let your breathing slow, and come with me to a high, quiet mountain where time itself seems to rest. High above the desert floor of eastern California, at altitudes between roughly 3,000 and 3,500 meters, there exists a forest unlike any other on Earth. The trees here are not tall, they are not lush. Many of them appear, at first glance, to be dead, their trunks stripped to bare, silvered wood by centuries of ice and wind. And yet, somewhere within that weathered form, a thin ribbon of living bark continues to carry water and nutrients from root to branch. These are the Great Basin bristlecone pines, Pinus longeva, and they are among the oldest known living organisms on our planet. Some of them have stood in this thin, cold air for more than 4,000 years. One individual, known as Methuselah, has been dated through careful ring counting to approximately 4,856 years of age as of recent measurements. There may be older specimens still, quietly unnamed, quietly enduring. Tonight, we will explore how these trees survive, what their rings have taught us about Earth's climate, and why their persistence across millennia holds lessons not only for science, but for the deepest questions of patience and resilience. To understand how a bristlecone pine can live for thousands of years, we must first understand the place where it grows, because the secret of its longevity is bound, almost paradoxically, to the harshness of its environment. The White Mountains rise along the western edge of the Great Basin, east of the Sierra Nevada. The soil here is dolomite, a pale calcium-magnesium carbonate rock that is alkaline and poor in nutrients. Most plants struggle to grow in dolomite. Bristlecone pines, however, have adapted to it over vast stretches of evolutionary time, and the scarcity of competition is, in part, what has allowed them to persist. Where other species cannot take root, there are no faster-growing trees to shade them out, no dense canopy to steal the sunlight. The bristlecones stand alone, widely spaced, each one a solitary monument in a landscape of white stone and thin air. The climate, too, is extreme. Winters bring heavy snow and temperatures well below freezing. Summers are dry and short. Annual precipitation is modest, often less than 30 centimeters. And the wind is a constant presence, scouring the exposed ridges, driving ice crystals against the wood with an abrasive patience that shapes the trunks into forms that seem almost sculptural. And yet, it is precisely this difficulty that serves the tree. In a milder, wetter environment, bristlecone pines would face fungal infections, insect infestations, and competition from faster-growing species. Here, in this high, dry, hostile place, the air is too cold and too arid for most pathogens. The bark beetle, which devastates pine forests at lower elevations, rarely reaches the bristlecone groves. The wood itself is dense and saturated with resin, which further resists decay. So the tree grows slowly, sometimes adding less than a millimeter of new wood in a single year. But it endures. Consider that for a moment. Less than a millimeter per year. A pace so slow it is almost geological. And in that slowness, there is a kind of strength that faster, more vigorous organisms never achieve. One of the most remarkable features of the bristlecone pine is its strategy of sectored architecture. Unlike many trees, which maintain a single continuous ring of living tissue beneath their bark, an old bristlecone pine may have only a narrow strip of living bark on one side of its trunk, while the rest of the tree is bare, silvered deadwood standing open to the sky. This is not a sign of dying, it is a strategy for survival. When conditions become harsh, when drought or damage kills part of the root system, the tree does not attempt to sustain its entire circumference. Instead, it retreats. It allows portions of itself to die, concentrating its limited resources into a single living sector, a strip of bark perhaps only a few centimeters wide, connected to a corresponding strip of roots below. This remaining sector continues to photosynthesize, to draw water from the thin soil and to produce seeds. The tree, in a sense, becomes smaller in order to stay alive. Scientists sometimes describe this as a form of modular dieback. and it is one of the key mechanisms that allows bristlecone pines to survive for millennia. A tree that tried to maintain its full canopy in the face of prolonged drought would exhaust itself. But a tree that can shed 90% of its living tissue and continue functioning with the remaining 10% has a profound advantage. It can wait. It can endure decades of poor conditions, and then, if moisture returns, slowly expand its living sector once more. There is something deeply restful in this idea, if you let it settle over you. The notion that survival does not always require growth, that sometimes the wisest response to hardship is not to fight harder, but to become quieter, to need less, to let go of what is no longer essential and protect only the vital core. The bristlecone pine has been practicing this wisdom for longer than recorded human history. It does not rush. It does not panic. It simply persists, one thin strip of bark at a time, breathing in the cold mountain air, year after year after year. Now, let us turn to what these ancient trees have taught us, because the bristlecone pines are not only marvels of biology, they are archives. Each year, a living tree lays down a ring of new wood, and the width of that ring is a record of the conditions the tree experienced during that growing season. A wider ring suggests a year of adequate moisture and warmth. A narrower ring tells of drought, cold, or stress. By carefully extracting a thin core from a living tree, a pencil-thin cylinder of wood that does not harm the organism, scientists can read these rings backward through time, year by year, century by century. This science is called Dendrochronology, from the Greek words for tree and time, and it was pioneered in the early 20th century by the astronomer Andrew Ellicott Douglas, who was originally interested in the relationship between sunspot cycles and Earth's climate. But it was Edmund Schulman, a researcher from the University of Arizona's Laboratory of Tree Ring Research, who in the 1950s turned dendrochronology toward the bristlecone pines. Schulman hiked into the White Mountains and began sampling the oldest trees he could find. In 1957, he discovered the tree he named Methuselah, which was then determined to be over 4,600 years old. Schulman published his findings in a landmark 1958 paper in the journal National Geographic magazine. But tragically, he died that same year at the age of only 49, never fully seeing the revolution his work would ignite. What followed was extraordinary. By cross-matching ring patterns between living trees and dead wood found scattered on the ground nearby, scientists were able to build continuous tree ring chronologies stretching back more than 9,000 years. This technique, called cross-dating, works because the pattern of wide and narrow rings in any given period is like a fingerprint of climate, shared across trees in the same region. A piece of deadwood with a distinctive ring pattern can be matched to the corresponding section of a living tree's record, and the chronology extends further into the past. These records have become one of the most important tools in climate science, a slow, patient archive written in wood. Perhaps the most profound gift of the bristlecone pine chronologies was the correction of radiocarbon dating. When the physicist Willard Libby developed radiocarbon dating in the late 1940s, a breakthrough for which he received the Nobel Prize in Chemistry in 1960, the method relied on the assumption that the concentration of carbon-14 in the atmosphere had remained roughly constant over time. If that were true, then measuring the remaining carbon-14 in an organic sample would give a straightforward estimate of its age. But the bristlecone pines revealed that this assumption was not quite right. By measuring the carbon-14 content of individual tree rings whose exact calendar age was already known from dendrochronology, scientists discovered that atmospheric carbon-14 levels had fluctuated over the millennia, influenced by changes in solar activity, Earth's magnetic field, and other factors. This meant that raw radiocarbon dates could be significantly off, sometimes by several hundred years. The bristlecone pine record provided the calibration curve needed to correct these errors. Today, the internationally accepted radiocarbon calibration curve, known as INTCAL, still relies in part on tree ring data, including bristlecone pine chronologies, to convert raw radiocarbon measurements into accurate calendar dates. This single contribution reshaped archaeology, geology, and paleoclimatology. Dates that had been accepted for decades were revised. Timelines of ancient civilizations were adjusted. The history of the last 10,000 years became clearer, more precise, more trustworthy, because of rings laid down, one per year, by trees growing in near silence on a cold mountain in California. And there is something deeply beautiful in this. That a tree, simply by living its slow, quiet life, recorded information that humans would not learn to read for thousands of years. The tree did not know it was keeping a record. It was simply growing, simply responding to the rain and the cold and the sun. And yet, encoded in its wood was a library of atmospheric chemistry that would one day transform our understanding of time itself. Let that thought rest gently in your mind as you breathe. There is a quieter, sadder chapter in the story of the Bristlecone pines, and it is worth telling gently because it holds its own kind of lesson. In 1964, a graduate student named Donald Rusk Curry was conducting research on Ice Age glaciology in the Snake Range of eastern Nevada near Wheeler Peak. He was studying the climate history recorded in the Bristlecone pines growing there, and he found one tree that appeared to be extraordinarily old. The tree had no name then. It would later become known as Prometheus. Curry needed a complete cross-section to count the rings accurately. Accounts of what happened next vary in their details, but what is known is that he received permission from the United States Forest Service to cut the tree down. When the rings were counted, the number was staggering. Prometheus had lived for approximately 4,900 years, making it, at the time, the oldest known living tree ever documented. And it had just been killed. The loss of Prometheus became one of the most significant events in the history of conservation, a cautionary moment that galvanized public awareness of the vulnerability of ancient organisms. In the years that followed, protections for bristlecone pine groves were strengthened. The exact location of Methuselah, the tree that now holds the record as the oldest known living bristlecone, is kept secret by the United States Forest Service, specifically to prevent a similar loss. No sign marks it, no trail leads to it. It stands somewhere among the other trees in the Methuselah Grove, indistinguishable to the casual visitor, protected by anonymity. There is a tenderness in that decision, a recognition that some things are too precious and too fragile to be made into landmarks. And perhaps, as you lie here tonight, there is comfort in the thought that not everything ancient needs to be found or named or claimed. Some of the oldest living things on Earth are best left alone, breathing quietly in the dark, known only to the wind and the stars and the slow turning of the seasons around them. Let us now consider the wood itself, because the material that makes up a bristlecone pine is, in its own way, as remarkable as the organism that created it. The dense, resinous heartwood of these trees resists decay to an extraordinary degree. Even after a bristlecone pine dies, its wood can remain standing for thousands of additional years, slowly weathered by wind and ice, but not consumed by rot or fungus. Fallen deadwood on the White Mountain slopes has been dated to more than 10,000 years old, and it still retains enough structural integrity for dendrochronologists to read its rings. This is possible because of the high resin content and the extremely arid environment. At these altitudes, there is simply not enough moisture to support the fungi and bacteria that would decompose a fallen tree in a wetter forest within decades. The wood dries, it hardens, it takes on the color of old bone, and it waits. Some researchers have described the bristlecone landscape as an open-air museum of wood, a place where the dead trees are almost as scientifically valuable as the living ones. It is the dead specimens that allow the tree ring chronology to reach so far back in time, bridging the gap between the oldest living tree and the deep past. Without them, we would have only the roughly 5,000 years of the oldest living individuals. With them, we can see back 9, 10, even 11,000 years, reading the climate record of the entire Holocene epoch, the warm period since the end of the last major glaciation. The Holocene is the age within which all of human civilization has unfolded. Every city ever built, every language ever spoken, every song ever sung has occurred within this window of time, and the bristlecone pines, both living and dead, have recorded the climate of nearly all of it. Imagine that thought settling into you now. like warmth spreading through tired muscles. A forest that has witnessed, in its silent, chemical way, the entire story of human culture. It did not watch, it did not listen, but it recorded, faithfully, in the language of wood. captures light from many directions throughout the long summer days. Even in this small detail, the architecture of patience is visible. Nothing is wasted, nothing is rushed. Every structure serves its purpose for as long as it possibly can. And in this way, the tree builds its life not through abundance, but through careful, deliberate, almost tender conservation of what it already has.